All right, so are you ready to dive into some seriously head-scratching math?
Oh, yeah. Always up for a good challenge.
Okay, well, we've got this document. It's called True or Fantasy for Podcast.txt.
Okay. Sounds intriguing.
And it's really taking on some of the, biggest ideas in mathematics.
Go well. Like what?
Things like, infinity, long-held proofs, and even proposing entirely new mathematical concepts.
Ooh, that's getting interesting.
It's pretty wild stuff.
All right, I'm hooked. Lay it on me.
Okay, so the author, they're really coming at this with a very,
The very what?
let's just say, unconventional perspective.
Unconventional, huh? I like unconventional.
But I think that's what makes this deep dive so interesting.
Okay, I'm ready. Where do we start?
All right, let's jump right into the first example.
Let's do it.
Euler's formula and the concept of infinity.
Euler's formula. Classic. And infinity. Always a mind bender.
Yeah, so Euler's formula.
Right.
It's this seemingly bizarre equation, right?
Okay, hit me with it.
Okay, so it's plus x cubed plus x squared
Okay.
plus x plus 1 plus 1 over x plus 1 over x squared.
Wait, okay.
Following plus 1 over x plus, and then it's, equals 0. ...
Yes, the infamous ellipses. Always a bit mysterious.
Right, and that holds true for any value of x,
Okay.
as long as it's not negative 1, 0, or 1.
Interesting. Interesting parameters.
Yeah,
Just looking at it.
I know.
Kind of makes my head spin a little,
Just a little bit.
Yeah, and that's where those dots come in.
Yeah, those dots.
They imply, an infinite series.
Right.
A progression that just goes on forever and forever and ever.
Yeah, forever.
Now, the formula, it seems to work, algebraically at least. But our author, they argue that it only appears to work because the concept of infinity itself is inherently, undefined.
So they're saying that the very idea of infinity is what makes this equation seem valid.
Precisely.
But maybe it's not actually true in a meaningful way.
That's the crux of their argument. They're suggesting it's kind of like a sleight of hand,
A mathematical sleight of hand. I like that.
We use this concept that we don't fully grasp to make this equation seem to work.
Okay, so.
But if you really dig deep into what infinity means, it starts to get really slippery.
Okay, but what does that even mean for us regular folks,
Right.
Like the people who aren't math whizzes.
Well, think about it this way.
Okay.
Have you ever, really tried to grasp what forever and ever actually means?
Forever and ever. Does it actually truly make sense on a practical level?
I get the general idea, but trying to wrap my head around actual infinity.
Right.
Yeah, it kind of makes my brain melt a little.
And that's precisely the point the author's driving at. Infinity, it's this concept, right?
It's incredibly difficult to truly grasp.
Yeah.
And maybe that's because fundamentally it's flawed.
Okay. All right, let's move on to another example.
Okay, sure.
Where the author really shakes things up.
I'm ready for more shaking.
Okay. They take aim at the idea that there are infinitely many prime numbers.
Oh, that's a big one.
Right, which has been a pretty well-established concept for a long time,
Yeah, it's a classic. The classic proof basically says that you can always find a new prime number, right? Based on the ones you already have.
Yeah.
So theoretically, the list just keeps growing and growing.
Forever.
But
our author, they have a problem with that logic.
They do.
Yeah.
They argue that the traditional proof,
Okay.
it only demonstrates the potential for a list of primes to keep growing. Not that an infinite number of them actually exist.
Okay.
And then they introduce this idea of big numbers.
Big number.
Yeah, big numbers.
Yeah. Okay.
Numbers so vast, they're practically impossible for us to even represent,
To even
to conceptualize, to even wrap our minds around.
Okay, so they're saying that big primes,
right.
these massive prime numbers we can't even fathom.
Yes.
Just don't exist.
Their argument is that big primes, they can't be identified or distinguished with the tools we have, for representing numbers. They call them big symbols.
Big symbols. Okay, so if we can't even conceptualize a number because it's so huge, does it really exist?
That's the question they're posing. Does it exist in a way that's meaningful to us?
Whoa. Okay, you're really making me think here.
It's a head scratcher for sure.
It makes you wonder, what does it even mean for a number to, like, exist?
That's the big question.
Right. Does it have to be something we can understand and write down? Or is there another way to think about it?
That's a great question.
It's like, I guess we humans, we're pretty limited in what we can grasp, huh?
We are indeed. Our minds, they're powerful, but they have their limits.
Okay. Well, all right. We're on a roll, so let's tackle another big one here.
Yeah, bring it on.
All right. Cantor, continuity, and this whole idea of the in-between.
Cantor.
Yeah.
Always a fascinating and often frustrating figure.
Now, Cantor's diagonal argument.
Right.
This is this famous proof about, like, different sizes of infinity, right?
Yes, it's one of the cornerstones of set theory.
So it's meant to show that the set of real numbers, all those numbers with decimals,
right,
that go on forever,
yeah,
they're uncountable.
Uncountable meaning
you could never, like, list them all out.
Right. You could never create a one-to-one correspondence with the natural numbers.
Even with an infinite amount of time.
Precisely.
But as we might expect, our author takes issue with this argument too, right?
They do. They dismiss Cantor's argument.
Okay.
As vacuous.
Yeah, vacuous. Okay.
Mainly because it hinges on that pesky concept of infinity we were talking about earlier.
So they see it as kind of like circular reasoning, right?
Yes, built on a foundation that's not really solid.
Okay.
And here's where things get even more interesting.
Okay.
They introduce a new concept.
Okay.
Called the in-between.
The in-between. Okay, what's the in-between?
It's basically a mathematical object, right?
Okay.
It's meant to represent continuity without needing points or infinite sets, which is how we usually think about it.
Yeah.
It acknowledges that numbers might not be the best way to understand something that's continuous.
So like a smooth, like an unbroken line that can't be broken down into individual points.
That's a great analogy. It's like this.
Okay.
This continuous entity that exists between those discrete points that we can represent with numbers.
Okay.
It's the glue that holds everything together, so to speak.
So if we zoom out and we look at the big picture here, are they suggesting that our current mathematical tools aren't, like, good enough?
It's a provocative idea, isn't it?
To truly understand, like, the continuous nature of reality.
That's a very astute observation. They seem to be arguing that our reliance on numbers and separate distinct sets,
right,
it might be limiting our ability to fully grasp the continuous nature of the world. It's
true. Think about it. Our experience of reality, it isn't a series of separate points, right?
Right. It's a flow, a constant flow.
It's this smooth and connected.
Yeah.
This whole in-between idea, it's making me think about how we experience the world in a whole new way.
It really highlights the potential limitations, right?
Yeah.
Of our current mathematical framework. And it encourages us to explore new ways of conceptualizing reality.
Okay. Let's move on to one final example.
Sure.
That really ties all of this together.
All right. I'm intrigued.
The Fundamental Theorem of Algebra.
Yes, a cornerstone of mathematics.
So this one states that every polynomial equation has at least one complex root, right?
That's what they taught me in school, at least.
At least that's what they taught me in school too.
Right.
But our author throws a curveball.
A curveball? How so?
By asking, what if we don't accept irrational numbers as legitimate solutions?
Interesting, because they're
essentially unidentifiable, right?
Yes, in their view, kind of like those big numbers we were discussing.
We were just talking about those big numbers.
Exactly, too vast, too unwieldy to truly grasp.
So they argue that irrational numbers,
yes,
which can't be perfectly represented as fractions or decimals,
right,
they don't really meet the criteria to be considered proper numbers.
It's a bold suggestion, to say the least.
And if you accept that premise,
right,
the fundamental theorem of algebra starts to crumble.
It does, doesn't it? Because so many polynomial equations rely on those irrational roots as solutions.
Exactly. So the author proposes that embracing this in-between concept could actually strengthen the theorem instead of breaking it.
Strengthen it. Interesting. How so?
Because then the roots of an equation could exist within these continuous in-betweens, even if we can't like express them perfectly as numbers.
It's like they're suggesting a whole new realm of solutions hidden within these in-betweens.
That's wild. So they're suggesting that by welcoming this new concept into our our mathematical toolkit, we might actually deepen our understanding.
Interesting.
Of these existing theorems.
It's definitely a bold proposition. And it leads to a really important question.
Okay, what's the question?
Could this in-between concept, right?
Yeah, this in-between.
Could it actually change how we approach and solve mathematical problems? Could it unlock new solutions and insights that we never even considered before?
It's certainly making me question some of the most basic assumptions I had about math.
Yeah, it's a real paradigm shift, isn't it?
There might be a whole world of numbers we haven't discovered yet because we're so focused on the ones we can write down.
It's like we've been staring at the trees and missing the whole forest.
Right.
That's the beauty of explorations like this,
Yeah.
They push us to look critically at what we think we know.
Right.
And to imagine new possibilities, to really expand our horizons and see the world in a new light.
So we've covered a lot of ground.
Yeah, we have.
In this document, True or Fantasy for Podcast.txt.
Quite a journey so far.
And the author,
right.
They have some pretty radical ideas about some of the most, fundamental concepts in math. I'm still trying to process everything we've talked about so far.
It's a lot to take in.
Yeah.
That's for sure. The author, they really go after some of the cornerstones of mathematics.
Right.
Like for example, they argue that infinity, the way we currently use it,
right,
it doesn't really make sense.
And they used Euler's formula and the idea of infinitely many prime numbers,
right,
as examples to show how our reliance on infinity might lead us to some shaky logical ground. I have to admit, I've always kind of taken infinity for granted, but maybe it's not as simple as it seems.
Right. It's one of those concepts that seems intuitive on the surface.
Yeah.
But when you really start to probe it,
yeah,
it can get pretty weird.
Yeah, and then there's the idea of those big numbers, right?
Those big
numbers so massive that they're beyond our ability to even represent them.
It's almost like they stretch the limits of what we can even conceive of as a number.
And the author seems to suggest that if we can't even conceive of a number, how can we really say it exists,
Right. It's like asking, does the largest cookie in the universe exist?
Oh, largest cookie.
Yeah. Just a fun thought experiment, maybe. But not necessarily question with a meaningful answer. Where would you even begin to look for that cookie?
Right. And the author, they apply that same logic to Cantor's famous diagonal argument.
Right.
Which is traditionally used to demonstrate different sizes of infinity.
Yeah, it's a pretty mind-blowing concept.
And they essentially say it's all based on a flawed premise.
They see it as building a grand structure on a foundation of sand.
And then on top of all that, they introduce this entirely new concept, right? The in-between.
Yeah, the in-between.
It's supposed to represent continuity.
Right.
In a way that goes beyond, traditional numbers and sets.
It's like there's this whole realm of numbers out there.
Yeah.
That we haven't even considered because we're so fixated on the ones we can write down,
It's almost like saying there's a whole spectrum of colors that we can't even see.
Exactly. It challenges our assumptions about what constitutes a number in the first place.
And it makes you wonder, right? Are we missing out on a whole new understanding?
It's possible.
Of math and maybe even reality itself. By sticking to the tools we've always used.
That's a great question, and I think that's what makes the author's perspective so valuable. Even if you don't agree with everything they say, it forces us to re-examine some of our most basic assumptions about math.
Yeah,
and its relationship to the world around us.
Okay, so we've talked a lot about the author's critiques and alternative concepts.
Right.
But I want to like bring things back down to earth for a minute.
Sure, yeah.
What does all this mean for someone who's not a professional mathematician, you know?
That's an important question.
Like why should they care about these seemingly abstract debates?
I think there are a few key takeaways here that are relevant to everyone, regardless of their mathematical background.
Okay.
First, it reminds us that even the most well-established areas of knowledge, they're always evolving. You know, what we consider truth today, it might be revised, or even completely overturned tomorrow.
It's a bit humbling to think about.
It is,
but it also makes things more interesting, wouldn't you say?
Absolutely. Second, this exploration, it really highlights the importance of critical thinking. It encourages us to question assumptions, even those that seem totally obvious, you know, and to be open to different perspectives,
right?
Even if they seem unconventional, or even radical at first.
Because as we've seen, sometimes those unconventional ideas, they can lead to like really, really groundbreaking insights.
Absolutely. And finally, I think this discussion, it shows us that math isn't just some dry, abstract subject that lives in textbooks. It's a vibrant, evolving field that's deeply connected to how we understand the world around us.
It's about how we think. How we reason, how we make sense of reality.
Precisely. It's a lens through which we view and interpret the universe.
And the author's willingness to question like the foundations of mathematics, even though it might be, you know, controversial. It ultimately helps us to understand the subject and its impact on our lives in a richer and more meaningful way.
I think that's a beautiful way to put it. It's about deepening our relationship with mathematics, seeing it not just as a set of rules, but as a way of thinking, a way of being in the world.
So if there's one practical takeaway from all of this, it's to embrace curiosity, question everything, and never stop exploring new ideas.
Well said. And I would add, don't be afraid to get a little uncomfortable. Yeah. You know, sometimes the most profound insights, they come from challenging our most deeply held beliefs.
Yeah.
The author of this document.
Yeah.
They're a perfect example of that.
You know, thinking about all this is really making me wonder. You know, thinking about all this is really making me wonder, are there other areas, you know, besides math? That could like benefit from this kind of radical rethinking?
It's a fascinating question.
I mean, what other truths, right? What other truths might we be taking for granted?
That's the $1 million question, isn't it? It really highlights the idea that the pursuit of knowledge, right? It's an ongoing journey, you know? There's always room for fresh perspectives. And challenging those assumptions we often don't even realize we're making.
Right. It's a little unsettling, but also kind of exciting.
Oh, absolutely. It's the thrill of the unknown, right? The possibility that there's so much more out there than we currently grasp.
So let's say for a moment that we we accept the author's ideas, right? About the limitations of traditional math.
Right.
Especially when it comes to things like infinity.
Okay.
Where does that leave us?
That's the big question. Where do we go from here?
What other ways could we approach these fundamental concepts?
Well, that's where things get really, really interesting.
Okay.
One possibility is to explore alternative, you know, mathematical frameworks that don't lean so heavily on the concept of infinity.
Okay.
For example, there's a field called finitism.
Finitism. Okay.
Which focuses on finite constructible objects rather than infinite sets.
So instead of dealing with these abstract, mind-boggling ideas about infinity, they're working with concrete, you know, tangible things that we can actually grasp and manipulate.
Exactly. It's about bringing things back down to earth, right? Dealing with the things we can actually see and touch and work with.
Okay.
And with infinitism, there are all sorts of creative approaches, to representing continuity,
right,
and dealing with the limitations of traditional number systems.
Okay.
Some mathematicians in this field have even developed, systems
yeah.
that avoid using irrational numbers altogether.
Wow. So they're essentially like creating new mathematical tools.
Yeah, that's a great way to put it. New tools for new problems.
Right. That are better suited to the kinds of problems that pop up when we try to wrap our heads around the infinite and the continuous.
Exactly. It's like we're building a whole new toolbox,
Whole new toolbox, yeah.
To tackle these really challenging concepts.
And these alternative frameworks, they might lead to insights and solutions, right? That were previously hidden from us.
It's like looking at a familiar landscape through a new lens and suddenly noticing details that you never saw before.
It makes you wonder, what other radical ways of approaching math, or any field of knowledge for that matter, right, might be out there waiting to be discovered.
I think that's a very real possibility.
Yeah.
Just look at the history of mathematics, right? It's full of these paradigm shifts where new ideas completely transformed our understanding of the subject.
Like the development of non-Euclidean geometry, for example.
Right.
It challenged centuries of assumptions about the nature of space.
Yeah.
And opened up all sorts of new avenues of mathematical exploration. It's mind-blowing to think about how how one new idea can just change everything.
It's truly remarkable. And who knows what other revolutions in thought, are just around the corner.
Yeah.
The important thing is to stay curious, stay open-minded, and always willing to explore new possibilities.
And to never be afraid to ask what if.
Exactly.
Even if it seems a little crazy at first.
Sometimes the craziest ideas are the ones that lead to the biggest breakthroughs.
Well, I think we've given our listeners plenty to think about today.
Oh, I think so too.
It's been a wild ride,
Yeah.
Through some pretty mind-bending concepts, but
it's been a journey.
I hope it's also been a thought-provoking and maybe even inspiring journey.
I hope so too. Yeah. The key takeaway here is that mathematics, it's not some static, unchanging subject, right?
Yeah.
It's a living, breathing field that's constantly evolving as we ask new questions,
right,
develop new tools, and explore new perspectives.
And sometimes, it takes a radical challenge to what we think we know,
right,
to push the boundaries of understanding and open up those new frontiers of discovery.
To shake things up a bit and see what falls out.
It's like shaking things up to see what falls out.
Exactly.
Well, on that note, I think it's time to wrap up this deep dive.
I think so too.
Thanks for joining us on this intellectual adventure.
Always a pleasure. It's been a great discussion.
And until next time, keep questioning, keep exploring, and never stop learning.
Couldn't agree more. Keep that curiosity alive, folks.